medical student. I'm going to be your PAL tutor today. We're going to be talking about alveolar ventilation. Oh, before I start, can you guys hear me clearly? And can you see the screen? I just need a thumbs up for somebody. Okay, so let's start. This is kind of a heavy topic. Oh, sorry. And I know, I think you guys took it over 3 lectures. It's pretty, I think it's pretty, it's comprehensive when you actually get to know it, but there's a lot of things that we need to go over. And I did change the order of the slides a little, just to help you better understand how it's going. So yeah, let's start. Okay, first of all, the slide. This is a pretty, you've seen this slide before, and basically what it's telling you is that, you take in oxygen and from the lungs, and it goes through, your circulation. First it goes to the lungs, and goes to the heart, and then it goes to the tissues. And as it's doing that, it's eventually the oxygen partial pressure is decreasing because the oxygen is being lost to the cells. And as it's lost, obviously the partial pressure is decreasing. By the time it gets to the tissue, it's around 45, something like that, okay? And as for, oh, sorry, this is CO2. I meant here. So yeah, you can see here, it's really high, it's 150. And then by the time you're at the tissue, it eventually gets to really low, okay? And the opposite happens for carbon dioxide. So at the tissue, you produce, by respiration, by various metabolic reactions, you produce carbon dioxide. And as it goes to the lungs, and it escapes through the lungs, your PCO2 eventually becomes super low, 0. Is that clear? Is that part clear? Okay, so now let's move on to the more important parts of this lecture. Okay. Now, imagine you have this container, right? And you have a bunch of these colorful balls, which are actually gas particles. And this is a mixed gas. And, you have all of these various different gases in there, and it exerts a total pressure. Okay, we'll talk about that. So now imagine I separate all of these individually colored molecules. So I have 4 different containers, and each of them have these molecules individually. Now, each of these different gases, it can be any gas, okay? These could be any kind of gas. They exert a partial pressure, okay? They have their own partial pressure. As the name suggests, partial pressure is, so you have a total gas mixture, right? Here. And partial pressure is the pressure that each individual type of gas exerts in that entire mixture. And we can calculate that. So we have, in this mixed gas, we have a total pressure, okay? It could be anything. It could be 100, it could be 150, it could be 200 millimeter mercury. And each of these individual gases exert their own partial pressures. And we can calculate this total partial pressure from these individual partial pressures. I mean, it makes sense, right? Because we said we have this in gas, we have this gas chamber, and it has all of these different gas molecules, different types of gases. And if we add them up, we get this total pressure, sorry. And yeah, so the equation you use for this is Dalton's law. So what I've done is throughout the lecture, throughout the session, I've highlighted the equations that you need to know. So some of the equations, they really just help you understand the equation that you really need to know. I've highlighted the ones that you really need to know, and I've added a slide at the end that will, show you all the important equations that you need to know. So yeah, so we have gas 1's partial pressure would be P1, gas 2's partial pressure would be P2, and gas 3's partial pressure would be P3, and gas 4's partial pressure would be P4. Now this can go on. You can have 100 different gases in one gas mixture, and you have to add all of them and get the total partial pressure. Now, let's, actually calculate it. So, for example, this gas, it has a partial pressure of 65 millimeter mercury. And this one has a partial pressure of 23 millimeter mercury. This one has a partial pressure of 15. And this one has a partial pressure of, 37. To get the total, what you do is that you add them, right? So you add 65, 23, 15, 37. So what would the total be here? Can somebody tell me? Just type it in chat. Or you can unmute if you like. Okay, 130. Almost. Okay. Yeah, it's 140. Right. So it's 140 millimeter mercury. Don't worry, like you can, there might have been like a mistake in the calculation, but yeah. So this would be a total pressure of 140 millimeter mercury. Okay. Yeah, don't worry about it. Now imagine instead of giving you, okay, ignore this for now, don't look at that. Instead of giving you the values for the partial pressure, I give you the percentage of gas that is inside this total gas mixture. So this is known as the fraction of gas, okay? For example, so now this pink gas, okay, it has a fraction of 46%, and this orange one has a fraction of 16%, and this yellow one has a fraction of 11%, and this green one has a fraction of 26%. And I give you the total pressure. And then I ask you to, for example, I want you to calculate if I want you to calculate just the partial pressure of this gas one, okay? And I have the total, and I want you to calculate this. How would you calculate? Can somebody do it for me? It's pretty simple, like, okay? Like you just have to multiply. So can somebody give me the answer? Yeah, so you multiply 140 by 46% or 0.46. And okay, so you'll get 65. It's right here, but yeah, you'll get 65. So essentially what you can do is that if you need to find the individual partial pressures, you can you just have to multiply it by the total. Or they'll tell you like, okay, what is the fraction of this gas in this gas mixture? And you can just divide the actual, so for example, like here, we had we had the actual partial pressure, and you just divide this by the total and you get a fraction. All right. Now imagine I say that the partial pressure is 100, but the fractions haven't changed. And this is a very important concept. I'll explain it more, but the partial pressures haven't changed. So can you tell me the partial pressures of each individual gas in this that will be if the total pressure is 100 millimeter mercury? Is anybody calculating? Okay, yeah, for 46. No, not 64.4. Okay, yeah, so 46, 16, 11, and 26, yeah. So basically how you calculate it is like this. So you have 100, that is your total total pressure, and you multiply it by the fractions. So this is 46%, right? So you multiply 100 by 0.46 and you get 46. And then you multiply 100 by 0.16 and you get 16. Now, again, it's easy because it's 100, but this could be anything. I could make it like 200, 367, whatever it is. And you can get the individual partial pressures of each gas. Is that clear? Or do I need to re-explain? Okay. Now this is a very important concept, and you need to understand this because Dr. Shams really emphasizes on this. The fraction of a gas in a mixture always remains the same. So you see how I changed, how I kept, even at 140, this was 46, this was 16, this was 11, this was 26. And even at 100, these values were the same. In a particular gas mixture, for example, we have atmospheric gas, right? The fraction of gases, and it will always remain the same. It is the partial pressure that changes. We have different gases. We have oxygen, we have water vapor, we have nitrogen, we have a bunch of different gases, and their fractions are fixed, but their partial pressures can change if the barometric pressure itself changes, okay? And this usually happens when there's changes in altitude. So if you go to a really high altitude, the barometric pressure will be different. But the fraction of a particular gas will always remain the same. Like, for example, the fraction of oxygen will be the same on the top of a mountain and at the beach, okay? It will always be the same. It will be the partial pressure that's different. Do you understand that? Okay, good. Wait, okay. Yeah, so so this is basically just these are some, I guess terms that you need to know. So fraction of inspired oxygen. Fraction of inspired oxygen is basically the fraction of atmospheric oxygen, because we inspire atmospheric oxygen, right? And the partial pressure of inspired oxygen is again the partial pressure of atmospheric oxygen, because we're getting oxygen from the atmosphere. And then you have a fraction of atmospheric oxygen. Yeah, partial pressure of atmosphere. Oh, okay. Yeah. So basically, they're all like the same thing. I just did it I wrote it here just so you know that they're the same thing. So don't get confused. Now, yeah, this is Dalton's law, and again, now we apply it, to atmospheric gas. So we have a bunch of, I mentioned, we have a bunch of gases in the atmosphere. We have nitrogen, we have oxygen, and we also have water vapor. Now, you might know this equation from high school or UPP if you took chemistry, but this is basically the equation. So X is a particular gas. So X could be oxygen, it could be nitrogen. So you have the pressure of X times the volume of it is equals to the amount of that gas times R is a constant and temperature, okay? This is for an individual gas. Again, it's written X here because it's meant to be for an individual gas. Now, for total gas, for the sum of all these gases, so for example, the sum of all atmospheric gases, you calculate, basically, you use this equation instead. So this is PB, which is barometric pressure, and you subtract the partial pressure of water vapor. Now, why do you do that? Because this says ideal gas law, right? And the water vapor is not an ideal gas. Okay, you don't need to know why it's not an ideal gas, but it's just not an ideal gas. So you have to subtract it. And we use this equation basically to get the partial pressure of a particular gas. If you want to get the partial pressure of oxygen, which is the most important gas to be in pulmonary, I use this equation. I can use this equation if I have the barometric pressure and if I have the fraction of that gas. And you have to make sure that you subtract water vapor partial pressure, okay? Because if you don't do that, it'll mess up your entire calculation. And yeah, there might be it might be a trick question to you. So you just watch out that you do subtract a water vapor's partial pressure. So this is basically just rearranging the equation to get the fraction. So how you get the fraction is basically, as I said, the fraction of a gas is the partial pressure of that gas over the total pressure. And the total pressure here, again, you subtract water vapor, is so total pressure is barometric pressure minus the water vapor's partial pressure, which is equal to the amount, which is also you can also get it by the amount of the individual gas over the total amount of all gases. So that is the fraction. Is that clear? So I feel like I kind of just mumbled a bunch of words, but is that clear? Because I can repeat it again, it's fine. Okay. Now let's move on. So imagine you're at the beach, okay? You're at the beach, you're having the time of your life, and it's it's a really good weather, and you're not having any trouble breathing. Now, why do I say that? Note that the barometric pressure at sea level is 747 millimeter mercury. And I tell you that the fraction of oxygen at sea level is 0.21. Can somebody tell me, can somebody calculate for me what the partial pressure of oxygen at sea level would be using these two values? Actually, wait, before I do that, yeah. So remember this. You have to subtract this. I forgot to give you the value for this, but yeah. So using these three values, what would you get? What would your calculation be? 147? Okay, let's see. So yeah, so use this equation and yeah, we get 147. Is this clear? Okay. Now imagine I take you to Mount Everest. Okay, I take you to the top of Mount Everest and you're really struggling to breathe. Now, why is that? I tell you that the altitude is, okay, this is the altitude, it's very high, The barometric pressure here is 247 millimeter mercury. I'm not going to give you the rest of the values. I want you to calculate the partial pressure of what do you call it? Oxygen based on what I've already told you. I know you can do it, okay? Okay. I got 42. Does anybody want to say, like, does anybody have any other answers? Or is 42 what we're going with? Okay. So, yeah, again, as I said, the fraction of oxygen will never change. As long as you're on Earth, as long as you're in the atmosphere, it's not going to change. If you go higher, fine, the barometric pressure drops. But the actual Okay, so I got a question that says, why does the partial pressure of water vapor stay the same at high altitude? The reason is because it's not an ideal gas. You don't need to get into the details of that. Just know that it's not an ideal gas. So it's always the same. So you don't have to worry like too much about, oh, like why does it not change? He's not going to ask you that, but he just wants you to remember that it's fixed, okay? And that is what I'm telling you here. So it's still fixed. So you still use the same value to calculate the oxygen partial pressure at a high altitude compared to like when you did it at a lower altitude. The only thing that's changing is the barometric pressure. The fraction of oxygen and the water vapor partial pressure will remain the same. And yeah, so you get 42 millimeter mercury, and that's a very low partial pressure, right? No problem. That's a very low partial pressure. And this is a big issue, especially for mountain climbers. I'm sure you must have mountain climbing itself is very difficult because you might think, oh, what if the person falls off? That is actually not even their biggest concern. Okay, maybe it is, but one of their biggest concerns is that there's so little oxygen that they can suffer from extreme hypoxia and they can die of that. So yeah, this is you probably might get a question like, oh, the person came to the ER after mountain climbing, and they might ask you to calculate the partial pressure of oxygen at high altitude, but they will give you the values like a barometric pressure. And okay, I would say if you can remember fraction of oxygen in atmosphere, because it might be given, I don't know if, or it might not be given, but it's just good to remember it. Like it's just helpful, it helps you really get through the question really quick. Now we're going to talk about respiratory exchange ratio. Basically, what this is that this is respiratory exchange ratio takes place in the lungs, okay? And what this is, it's a calculation of carbon dioxide output over oxygen uptake, okay? The volume, so you usually use volume to calculate this. Now, why did I put this? Okay, so I put these two equations twice, right? Why did I do that? Okay, the reason is that usually, for example, for carbohydrate metabolism, I'm sure you've seen this equation along, like in mole, maybe in high school. But you see, you have 6 carbon dioxide molecules produced for every 6 oxygen molecules that you consume. And you divide carbon dioxide over oxygen and you get a ratio of 1. Essentially, you would use you could use volume here, but it's just a ratio, so it doesn't really matter if you use volume or if you use these 6/6. Okay, if you use the carbon dioxide molecules over oxygen molecules, it's the same thing. But the only difference between respiratory exchange ratio and respiratory quotient here, which is again which is basically this 6 carbon dioxide over 6 oxygen, which we got from this equation, is that this respiratory exchange ratio takes place in the lungs and this takes place in the tissue. And ideally, during a steady state, when you're normally breathing, you're not doing anything, you're just resting, these two values are equal. So respiratory exchange ratio and respiratory quotient are equal. Okay, but they will deviate from each other during unsteady states. These don't have to be pathological states. This could be you're just exercising, or you're holding your breath on purpose, or you're crying. Hyperventilation, hypoventilation, we'll talk more about that later in the session. And yeah, so I just wrote it that R is calculated at the level of the lungs and RQ is calculated at the level of the tissues. This is all you need to know, but is this clear to you? Also, one more thing. So for proteins, RQ would be 0.8 because you produce less carbon dioxide compared to oxygen. And for fats, it's even less. It's 0.7, okay? Is this clear to you, or should I explain it again? Okay. Now let's move on to the next slide. Now I have two compartments, okay? I have this large gas chamber, but I have divided into two compartments. I have this little barrier in the middle, and in the first compartment, compartment A, I have a particular gas. Let's call it purple gas, okay, just to make it easier for us. And in compartment B, I have this orange gas, okay? Now, what do you think will happen if I remove this barrier? Okay, yeah, they'll mix. So they'll mix. Why would they mix? Like there's a reason behind mixing, and like, yeah, you're right, but why do they mix? Exactly, airflow. Okay, not air, the gas. The gas flows to be in equilibrium. So basically, there is this partial pressure gradient for each gas. And this gas will tend to move there because it wants to like be in equilibrium, right? It wants to be spread out evenly throughout this entire compartment, because now this is one compartment. It's no longer A and B. And this gas wants to do the same. It wants to equilibrate. So that's what they'll do. They will have an equal partial pressure in each compartment. So they'll equilibrate. So basically now this was compartment A and this was compartment B. It will have compartment A will have equal partial pressures, or like not partial pressures, but it'll have, okay, so compartment A and compartment B will have an equal fraction of gas purple, and compartment B will also have a compartment, and again, A and B will also have equal partial pressures of gas orange, okay? And why did I tell you that? Now, imagine we're in the alveolus, right? This is your alveolus, and this is your pulmonary capillary. Imagine I barred this place off. So I have a barrier here. I didn't, I don't allow any gas exchange to take place. And what's happening is that atmospheric gas is coming in and it's going out. It's coming in and it's going out. There's no gas exchange. What happens is that eventually, because the alveolus is open to the atmosphere, the alveolar oxygen fraction, or our oxygen partial pressure, becomes equal to the atmospheric partial pressure. To the point, like, so it's all the same. So for example, if I have 6 oxygen molecules in the air, I'll have 6 in the lungs, 6 in the alveolus, and then I'll also breathe out 6. So it's all in equilibrium, okay? Does that make sense? Okay, good. And here I said, similarly, arterial gas partial pressures would be equal to venous gas partial pressures. That's the same concept, because look, we're no longer having any gas exchange. And because okay, I'll show you in this slide. Okay. We're no longer, never mind, we're no longer having any gas exchange, and the veins and the arteries are connected through the capillary beds. So essentially, they'll also equilibrate, okay? And so yeah, basically this is what you would see in the alveolus, because it's barred off, and the capillaries, so they have their own part. They maintain whatever they're doing. Okay, that's a little confusing. Ignore that. Okay. But yeah, so I was talking about the veins and the arteries, right? So imagine like they're connected. This is your capillary bed, and you're allowed to, transport gases freely. You don't, and there's no gas exchange. So their composition doesn't change. It doesn't change. And you can have like free mixing, basically, kind of, and you have equal partial pressures of the gases. That makes sense? Okay, so again, this is in the case of no pulmonary gas exchange. Now imagine I do have pulmonary gas exchange. This place is no longer barred off. And now it gets a little more complicated, because not only do you have the alveolus to the outside, but you also have the alveolus to the capillaries. So let's start with the alveolus to the outside. Basically, now since you have gas exchange, essentially you're not going to have the same compositions. So you're going to breathe in something, and then you're going to breathe out something. And in the capillaries and the veins and the arterioles, venules and the arterioles. So you have 2 oxygen molecules and you have 4 carbon dioxide molecules, because the blood coming through the pulmonary venules is richer in carbon dioxide compared to oxygen. And in this alveolus, you have gas exchange. So you gain oxygen and you lose carbon dioxide. And now you have, a changed composition of, blood in the pulmonary capillaries, and then it goes to the pulmonary arterioles. And now you have blood that is richer in oxygen and less rich in carbon dioxide, okay? Now I lost oxygen and I gained carbon dioxide. And I like exhale a different kind of composition of gas. Now we can actually calculate alveolar partial pressure by looking at this entire diagram. It helps us because basically what you inhale and oxygen you inhale is that's already coming in, but you also gain carbon dioxide, and that kind of replaces this oxygen. So you have to take that into account. You can't just calculate you can't just say, oh, alveolar oxygen partial pressure is just equal to the atmospheric pressure, because now you're taking into account the fact that you have gas exchange. If you didn't have gas exchange, yeah, you could say, oh yeah, alveolar partial pressure of oxygen is equals to inspired partial pressure of oxygen or atmospheric partial pressure of oxygen. But now you have a gas exchange, so you take that into account. Now, why did he write R here? The fact, if you recall earlier, we said that R was the respiratory exchange ratio. So it's basically carbon dioxide output over oxygen uptake. I said if you're in a steady state, this is equal to 1. But now, I would really recommend that you do usually use this, because a lot of people don't use it. If it's 1, but it's just good to remember. So I'm just gonna explain this. So if R is equal to 1, then so you want to calculate oxygen alveolar partial pressure. As I said, it's inspired oxygen partial pressure minus the alveolar carbon dioxide that you got from the capillaries. And inspired, we calculated earlier, it was 147. This is if you're, at sea level. And usually this value will be given to you, so you don't have to worry about it. And alveolar carbon dioxide, this is usually 40. Okay. Okay, wait. Okay, this was supposed to be an equal sign, so ignore. That's not supposed to be a subtract sign, but that's supposed to be an equal sign. So you get 104. Now, if R is equal to 1. Now, if R is not equal to 1, if R is less than 1, it'll never be more than 1. If R is less than 1, then you use this equation. And I said I recommend that you always use this equation, even if R is equal to 1, because it just helps you remember that you have to make sure you take R into account. So again, our inspired oxygen partial pressure is 147, and we subtract 40 over 0.8. Now, this is if you have proteins, okay? If you recall, I said that for proteins, our R is 0.8, and then you'll get 97 millimeter mercury, so it's lower, okay? Now, what would the oxygen partial pressure be during prolonged fasting? This requires you to think a little, but just think about it for a second. Okay, since I've gotten no responses, I'll just say myself. Okay, during prolonged fasting, recall, I don't know if you've taken this in mole yet, but you use fats, okay? I think you still need to take it, but you use fats during prolonged fasting. And for fats, our R was 0.7. So now we plug that into this equation. Can somebody calculate what the oxygen alveolar partial pressure would be if our R is 0.7? You already have all the values you need. You just need to plug it into the equation. Okay, I got 90. Let's see. Actually, don't remember what it was. Yes, it's 90 millimeter mercury. Is this clear? This is all I really need to really need you to know from this part. Is this clear? or do you want me to go over it again? Okay. Now, what's basal metabolic rate? This is basically metabolic rate itself is your demand for oxygen uptake. Basal metabolic rate is your demand for oxygen uptake at rest, not while you're exercising, not while there's an unsteady state, during rest. And basal metabolic rate is actually equals to VO2, which, okay, so this basically means time, okay? So the dot means time, so basically means oxygen ventilation. So BMR increases by 10% with a 1 degree increase in temperature in degrees Celsius, and it decreases by 10% with a 1 degree decrease in temperature in degrees Celsius. Make sure like you use degrees Celsius because it's different for Fahrenheit. So now if I have a BMR of 300 milliliters per minute at 36 degrees Celsius, imagine I increase the body temperature to 37 degrees Celsius. So what will happen? I mean, it's written here, but what will happen? Just like tell me. It's I already said it, but just tell me. Yeah, it increases. And it increases by 10% because I increase the temperature by 1 degree. So 37 minus 36 is 1. I increase the temperature by 1 degree, and with the 1 degree increase in temperature, my BMR increases by 10%. So to get the new BMR, what I'll do is I'll add 300 times 10% to the original BMR, which was 300, and I get 330. Now, similarly, if I decrease the temperature by one degree, I would have to decrease my BMR by 10%. So what I would do is that I would multiply 300 by 10% and subtract that value from 300, which was my original BMR, and I'd get 270, okay? Now, maximum oxygen uptake. So for basically what you need to understand here is that when you're increasing, so every 1 degree, yeah, so 1 degree change of the temperature gives us gives us a change by 10% for the BMR, right? Yeah, that's what it does. Would BMR be high when exercising? Yeah, okay, so if your body temperature is increasing, your BMR does increase, and that's what we're talking about here. So I said VO2 is BMR essentially, and when you're working, I mean, by work, I mean when you're expending energy, like exercising or doing anything like that, like taking part in any aerobic events. I say aerobic because you're using up oxygen, right? So your BMR would have to increase to meet those increased energy requirements. The average BMR for adults is around 300 milliliters per minute. For athletes, it's higher because they work out a lot, so they have higher oxygen requirements. Is this clear? And this is just a graph. So basically shows you, okay, as your work rate is basically energy, energy. As it's increasing, your BMR also increases. At some point, it reaches a maximum because after that, you really cannot increase it anymore. But yeah, so it's increasing, and then you reach a maximum, and then you can't increase it anymore. Is that clear? Okay. Now we're going to talk about carbon dioxide. Okay, I'll explain it again. This slide, right? Or do you want me to explain the previous slide too? Okay, so what I said is that, okay, here. So here I said that BMR is equals to VO2, right? Okay, and what happens is that BMR or VO2 increases with increased energy expenditure. So when do you expend energy? You expend it during exercising, especially during very strenuous exercise, or when you're yeah, like essentially like exercise is one of the major things, right? And as it's increasing, you also have to increase your oxygen uptake. It makes sense because if you notice, like when you're exercising, you like breathe really, you breathe more faster, but yeah, so because you need to you make more ATP, which is very mole, but don't worry too much about that. But your BMR would increase when you're working. Again, work means energy expenditure because you want to meet your increased oxygen requirements. Okay, does that make sense? Okay. Let's talk about carbon dioxide exchange now. So we said that we can calculate alveolar oxygen partial pressure by, like PiO2 and then PaCO2. Similarly, we can also calculate PaCO2. So thing is that you actually don't inspire any carbon dioxide from the air. Hypothetically, you do not get any carbon dioxide from the air itself. So it actually is produced in your body and then it's lost in the air. So it has a very, strong concentration gradient, and it favors leaving the alveolus and going into the atmosphere. So what happens is that you gain it into the alveolus, and then you use this equation. So this is a VCO2 over ventilation, total alveolar ventilation. So the ventilation, so the loss of CO2 over total alveolar ventilation multiplied by this constant. You don't need to know what this where this constant comes from. Just remember this value, 863. Don't worry too much about what this value is. It's just a constant that you need to know. So again, it says here PaCO2 is the carbon dioxide partial pressure of alveolar gas and is nearly identical with PaCO2 of arterial blood. Again, because you only get it from the blood, you don't get any from the outside, right? And PaCO2 is linked to the metabolic carbon dioxide production and alveolar ventilation. Alveolar CO2 was derived from the blood as a product of metabolic reactions, and alveolar ventilation eliminates the CO2. So this is very important. Alveolar ventilation eliminates CO2. And we'll see this more, and you can see here. So PaCO2 is inversely proportional to alveolar ventilation. So if I increase alveolar ventilation, I would decrease PaCO2. Okay. Now, this is the equation that you need to remember. It's here, but yeah, just remember, you need to remember this equation. So VCO2 and alveolar ventilation differ slightly from person to person. Not too much, usually they'll give you the value if they want you to remember, if they want you to do the calculation. So people who have depressed brain stems will have decreased alveolar ventilation, but normal VCO2. Okay. And what do you think the consequences of this would be? Imagine this is decreased, this is normal. What would happen to this? What would happen to your PaCO2 if you decrease your alveolar ventilation? Okay, yeah, it'll increase. And yeah, so if I decrease this, wait, sorry, this was supposed to be increased. I don't know. Ignore this. I'll fix this. But yeah, this will increase. Okay, ignore this, please. And if I increase my alveolar ventilation, it will decrease. Yeah, so this is supposed to be decreased, it's supposed to be increased. All right. Now I gave you these values. Can you calculate PaCO2 for me? And you have the constant here. Just use your alveolar ventilation is 86.3 and your VCO2 is 225. $2,250. Okay. Do you have any other answers? Okay, I don't think we have any other answers. So yeah, so you get 2,250 milliliters per minute. This is, I think that, yeah, this is your average, this is a person's average PaCO2 based on, if you have alveolar ventilation of this and you have VCO2 of 225. And now we have it in graphic form. Graphs really help you understand, and I would really recommend you go over this graph again even after the session and while you're studying, because it really helps you understand. Now this is quiet ventilation. Okay, at this level, your alveolar ventilation rate is approximately 4, I think. Not 4, not even 4, it's nearly 5. And your PaO2 is it should be here at 100, I think. And this is PaCO2 is at 40. Now, if I increase alveolar ventilation, according to our equation, if we increase alveolar ventilation, we decrease PaCO2, and that's what happens. So your PaCO2 decreases. your PaO2 increases, okay, because you have like like you're taking in more oxygen. But yeah, so your PaO2 increases, but your PCO2 decreases. And at very when you have hyperventilation, as the name suggests, when you're ventilating like quite a lot, your ventilation is super high, you're gonna have very low PaCO2 and a PaO2, like, okay, yeah, it'll be high, but what's more important is PaCO2 will be lower. And if you have hypoventilation, which is lower than normal ventilation, then your PaCO2 will increase quite a lot. Like, see, it's like all the way up to, I think, 70 here. And your oxygen PaO2 will also decrease. Okay, is that clear? This is based on this equation here. Okay. Now let's talk about, like I said, hypoventilation, hyperventilation. How do you determine, what that is? So basically, normal ventilation is normal alveolar ventilation, which means that PaCO2 is within normal ranges. So we don't really get it from PaO2, even though, yeah, it changes PaO2, but what our main concern with hyper and hypo and normal ventilation is PaCO2. So at normal ranges is like around 40 millimeter mercury, 40 millimeter mercury. And then hyperventilation is increased alveolar ventilation. We said that if we increase alveolar ventilation, our PaCO2 decreases. So it's below normal. So it would be like, anywhere below 40 millimeter mercury, not like 39, that's too close, at least like 10 to 15 millimeter mercury change. Like you'll be given, the value, I guess the ranges if you need to like determine whether it's hyper or hypoventilation. So yeah, your alveolar ventilation increases, usually like it'll double, and this happens, like in excess metabolic needs such as drug toxicity, high altitude hypoxia, anxiety, pregnancy, metabolic acidosis. So like high altitude hypoxia, we already discussed that when you go to high altitudes, your the oxygen partial pressure in the atmosphere is very low. And because it's very low, again, I told you on this graph here that, like hyperventilation increases your alveolar oxygen partial pressure. So you basically at high altitudes, you would be hyperventilating to try to get enough oxygen into your body. And because of that hyperventilation, your PaCO2 would decrease. Yeah, anxiety, usually people have panic attacks. They can, like you've probably heard of the term like, oh yeah, the person is hyperventilating. So yeah, that's what happens in pregnancy due to progesterone and metabolic acidosis. You don't need to know much about this. Metabolic acidosis, you'll learn about this more in renal. Don't like worry too much about it. These are just like some common causes. And he mentioned this in his slides. That's why I added it. And then you have hypoventilation, which, as the name suggests, is decreased alveolar ventilation. So your PaCO2 would not increase. It would be above 40 millimeter mercury. And he didn't add the causes, but I just thought like I'd give you an example of what happens. Like you could have this in chronic obstructive pulmonary disease, COPD, and CNS disorders, trauma, obesity, etc. Okay. So is this clear? Alveolar ventilation. Okay. Now we've come to the last part of the lecture, and this is going to be kind of complicated. Okay, this is a little bit of a complicated part, and but I really need you guys to be with me. I'm going to try my best to explain it as simply as I can. This is your alveolus, and this is your dead space. Okay, you guys know what dead space is, right? Your anatomical dead space. Yeah. Okay, what is it? Exactly. There's no gas exchange there. And it has a fixed volume. For an average adult, the alveolar volume is 3 liters, okay? And 5% of this alveolar volume is dead space volume, and 5% of that is like 150 ml. This says here before inspiration, just after expiration. So you're just like at this point, you have your functional residual capacity, which is basically your expiratory reserve volume and your residual volume. And they're all both individually 1.5 liters. So that's a total of 3 liters. And then I said 5% of that is 150 ml, which is your dead space, anatomical dead space. Here, no gas exchange takes place. whereas in the alveolus, gas exchange takes place. Now, I wanted to let you know that basically the composition of gases in the alveolus and in the dead space is the same. I just color coded this different because I'm gonna like try to explain this on the next slide, and this is gonna come in here. So I just wanted to I wanted you to be able to differentiate them. So I said here, equal partial pressures of gases in alveolus and dead space because they're open to each other, and then they equilibrate, so their gas composition and the partial pressures of the gases are equal. Okay, there's no gas exchange in dead space, so its gas composition is equilibrated with atmospheric gas during inspiration and with alveolar gas during expiration. So this is after expiration, right? So now it's equilibrated with alveolar gas. Now, this is after you inspire. So you take in a bunch of fresh air. This gray part is your fresh air. And I said that the dead space volume, if we're going for like 3 liters total alveolar volume, is 150 ml. And this is a fixed value, okay? This will never change. It will always be 150 ml. It will never increase. It will never decrease. Whereas for the alveolus, yeah, the alveolar volume can increase, decrease, okay? And that is what happens. So you, for example, if your normal tidal volume is like 500 ml, okay? And imagine I take in 500 ml. So this, the alveolar volume increases by 500 ml, but there's a catch. Not all of that 500 ml that came into the alveolus is fresh air. 150 ml of that is this gas that was here in the dead space earlier that has now moved into the alveolus, and 150 ml of the fresh air is now remaining inside of the dead space, okay? And basically, how you calculate tidal volume is you subtract dead space volume from the tidal volume, and how you calculate alveolar volume is you subtract dead space volume for tidal volume and for the fresh air, okay? So the alveolus only gets 350 ml of tidal volume. Yes, it increases by 500 ml, which is our tidal volume, but 150 ml of that is the volume that was already in the dead space here, okay, at the end of expiration. Is that clear? Because like the entire concept is really based on you understanding that part. I can repeat it again, like I really don't mind. Okay, is it clear for everybody? So only 350 ml is per gas exchange, right? What do you mean by that? I'm not sure I understand what you mean. In the alveolus? Okay. So basically, like here I said it's mixing, right? And it ends up mixing. Any gas that is in the alveolus will go through gas exchange. Basically, what will happen is that the fresh air and this gas, this that was in the dead space, they will mix, and there will be gas exchange. I wouldn't say that there would be no gas and like only 350 ml is for gas exchange. We're getting here is only 350 ml of the gas that comes into the alveolus as fresh air. Is that clear? Is that clear? Does that answer your question? Okay. Okay, so I said yes. Now, again, we have this equation that you need to know. And yeah, you need to know the highlighted part. But also, I forgot to highlight this, but I think you also need to know this because I saw this in some of your in some of some questions. So I would recommend you know this, and this is the key for them. So basically, tidal volume is equals to dead space volume plus alveolar volume because it gets divided between the two, right? And to basically, alveolar volume we said was tidal volume minus dead space volume, and that is VA. And if I multiply by the respiratory frequency, I can actually get to total ventilation and ventilation of dead space and ventilation of the alveolus. And essentially, I get this equation. So if I want to get the ventilation in the alveolus, I can subtract dead space ventilation from total expiratory ventilation. Okay, is that clear? Okay. Now, after you've inspired, okay, so like now this gas has been mixed. There's been gas exchange taking place. This is used now. This is used alveolar gas. It has carbon dioxide in it, and it's just like not fresh anymore. This is still fresh because, again, why? Because there's no gas exchange in the dead space, right? Yeah, so that's all I need to know here. Now we expire, okay? So there's expiration taking place, and you expire, so you get rid of 500 ml again, and in that 500 ml, so you have the alveolar fraction, and then you have the inspiratory fraction. Why do I say inspiratory fraction? Because this is literally the same thing as what you inspired, because there's no gas exchange here, so this is essentially the same kind of gas that you inspired initially. And this is the sum of inspiratory fraction and alveolar fraction is your tidal volume, the one that you inspired in the beginning, right? Alveolar fraction, we said we can calculate the alveolar volume by VT minus VD, right? So that's that. And then inspiratory fraction is VD, okay? And now you have these two mixing. Okay, so the alveolar fraction, the inspiratory fraction, they're mixing, and you get the total mixed expiratory fraction, which is again equals to tidal volume. Okay? Is that clear? Okay. Now we have this equation. Excuse me. We have this equation, and this was our alveolar volume, and we multiply by that by the alveolar fraction, and then we add the dead space volume, and you multiply by that by the inspiratory fraction, okay? And then we get this equation, okay? So we get, this is equal to the tidal volume times the total expiratory fraction. Again, this is reflecting what we saw here. So if this VT minus VD, we multiply that by this, and then we multiply VD by FI. This is the sum of this, okay? So FE times VT. And now if you rearrange this equation, you get this. So you get VD over VT, right? And what that is that you, for oxygen in particular, you can subtract alveolar fraction from the expiratory fraction, and then you divide that by the inspiratory fraction, and from that you subtract the alveolar fraction. This is for oxygen. Now for carbon dioxide, there's no inspiratory fraction because I said that you do not inspire any carbon dioxide, right? And you can do the same. This is the exact same thing. You can just, like plug in partial pressures instead of fractions. And yeah, you get the same equation. You don't need to remember this equation. He just put this in here to help you understand what he's saying. Don't remember it. And if he says don't remember something, really just don't remember it. Just ignore this. You don't even look at it. Honestly, yeah. So is that clear? Okay. Now, these are all the equations. We've come to the end of the lecture. It's actually surprisingly very, quick. Do you want me, before we go to questions, because I do have a few questions like that I compiled for you, do you want me to go over anything again? Because I can go over the whole lecture if you want. I really don't mind. I know it's a lot, a lot of different concepts that we took. We took a lot of equations. Is there anything that you need me to revise? I really don't mind going over it. Okay, so let's solve question now. Okay, at a fraternity party, a 17-year-old male places a paper bag over his mouth and breathes in and out of the bag. As he continues to breathe into this bag, his rate of breathing continues to increase. Which of the following is responsible for the increased ventilation? It's a pretty straightforward question. Okay, you already got an answer. B, okay. Do you have any other answers? It's fine if it's okay if you're wrong, just say it. Don't worry about it. B, okay. One more. Okay, B. So yes, it's B, because if you increase ventilation, if you increase PCO2, you increase your ventilation, right? Because you want to counter the effects of increased PCO2. Next question. Which diagram best describes the relationship between alveolar ventilation and arterial carbon dioxide tension when the PCO2 is arranged acutely over a range of 35 to 75 millimeter mercury? Okay, so we got F and we got A. Okay, let's see. So the answer is F. Essentially, as I said, when PCO2 increases, your alveolar ventilation increases because you want to get rid of that PCO2, right? I thought there was an equation here. Never mind. Okay, so your alveolar ventilation increases to counter the effects of increasing PCO2. But here for A, if your alveolar ventilation increases, you wouldn't really, if your PCO2 increases, you wouldn't really want to decrease alveolar ventilation, right? Because then like you would just be like in an endless cycle of increasing PCO2. So does that make sense? Okay, next. A normal subject, his PaCO2 is 40 millimeter mercury, voluntarily doubles his respiratory frequency, but does not change his tidal volume. Assuming no change in metabolic rate, when he comes to a new steady state, his PaCO2 is most likely to be... Okay. Okay. So yes, the answer is B. And wait, okay, so you use this equation and yes, you use this equation, and if you're increasing your, so this again, this is respiratory frequency times volume of alveolar volume. So if you increase your if you double your respiratory frequency, this will have, according to math, right? So yeah, you don't like actually need the rest of these values. You could just like, it's basically like getting a ratio. With no change in respiratory minute volume, respiratory minute volume is the respiratory frequency. I think it's alveolar, respiratory frequency. The alveolar ventilation rate may be increased by an increase of... Okay. I got one answer. Where's my other loyal supporter? Okay, D. I got D. So yeah, it's D, according to this equation. So you see like how you can use these equations to actually answer these questions, even though there's no values involved. It's just like, like, okay, if this increases, that decreases, and that decreases, this increases. And this is our last question. I believe it is, yeah. A person's normal VT tidal volume is 400 milliliters with a dead space of 100 milliliters. The respiratory breath rate is 12 breaths per minute. The person undergoes ventilation during surgery and the tidal volume is 700 with a rate of 12. What is the approximate alveolar PCO2 for this person? That one got you thinking, huh? Okay, so I have an A. I have no idea. Okay, let's see. Oh, yes, the answer is B. And this is the explanation. So you use these two equations. Normal alveolar PCO2 is 40 millimeter mercury. So yeah, okay, that's kind of on them where they want you to like, that the alveolar PCO2 is 40 millimeter mercury. And that's why I say, like, it's just good to remember these values because some questions, like practice questions, require you to know these already. The normal alveolar ventilation for this person is 3.6 liters per minute. On the ventilator, the VA is 7.2, so it doubles, right? So if your alveolar ventilation doubles, your PaCO2 halves, so it will be 20. Is that clear? Okay, now that's the end of my lecture. I mean, my session, sorry. If you have any questions, please let me know. Thank you for attending, and please scan this QR code for GND. They're very lovely people. And I think there's going to be a feedback form for them. So yeah, you're welcome. If you have any questions, I'll send you the slides, and I've attached my number at the beginning at the first, basically the introduction slide. You can reach out to me. I'll be more than happy to answer your questions. And good luck on your exam. You have a whole week to study. You have a break. Use it wisely. Inshallah, you'll do very well. Don't worry about it. The questions are the questions, like for us at least, they were pretty straightforward. Do a lot of practice questions. Make sure you understand the concepts, especially for physiology. And yeah, good luck. And I hope you enjoy your winter. Make sure you scan this though. Okay.